Hello everyone and welcome to this lecture in the hands-on large language models series. From the previous lecture we have started looking at a very important concept, and that is called as semantic search and RAG. We saw that within semantic search itself there are three broad categories regarding how we can use language models for search. The first is dense retrieval, the second is re-ranking, and the third is retrieval augmented generation or RAG. Why are we learning about all these methods? Because search has now moved from a keyword based search to semantic search. What's the difference? In keyword search we just look at matching the words and then give appropriate searches. So let's say if I go to Google right now and if I search that shows like Stranger Things, okay, if I want to watch shows like this, in keyword search we'll just look at keywords like stranger or things and then the results will be based on this. But that's not what I usually want. I want the search engine to understand the meaning of what I have said. When I say shows like Stranger Things, I actually mean shows which have a mystery component to it, shows which are set in a small town or small village and are very engaging. So I want my search to understand the meaning. That's where semantic search comes into the picture. So as has been defined over here, searching by meaning, that is called as semantic search. And ever since transformers were discovered, the BERT model came into the picture, search has been completely transformed. So now whenever you use Google, we are always doing semantic search. You might not be knowing it, but we have transitioned from a keyword search which happened 20-25 years back to semantic search by default now. But since language models are becoming so much popular, there are different methods of semantic search which have been developed. The first is dense retrieval, the second is re-ranking, and the third is RAG. In today's lecture we are going to look at this first system over here. So let me just change my color a bit, which is called as dense retrieval. We are going to understand what dense retrieval is, how it can help our search, and how language models are utilized in the process of dense retrieval. This is going to be a lecture which is combining theory plus practical. Later we will also go into some interesting concepts such as chunking, for example. You might be thinking what exactly is this concept right now. We'll go into it in detail. And we'll also look at fine-tuning the search process. Towards the end of the lecture, we'll devote some time to these two concepts because they are also pretty important. So let's start with dense retrieval right now. I'll explain dense retrieval to you in a very simple way. So in dense retrieval, what happens is that let's say the user puts a query and the query shows like Stranger Things, right? So let me write it down here. Let's say the query which the user such as me has asked is shows like Stranger Things. That's the query, right? What's done in dense retrieval is that this query is taken and this is converted into a vector. This process of converting query into a vector is also called as creating a vector embedding. So this is a fancy way of saying this text is created or converted into a vector. It's also another way to say it is that we create a vector embedding for this particular query, which means that the text is taken and the text is converted into a higher dimensional vector space. So let's say this query can be taken and it can be converted into a 384 dimensional vector, just as an example. Now the space where this query is projected, it's not a random vector space, it's a space where words carry meaning. So two vectors will be closer together if they are similar in meaning to each other. So we are going to use something which is called as an embedding model to convert this query into a vector. So I'm just going to write this over here. We will use something which is called as an embedding model, and this embedding model is a large language model. This is a model which there are several different embedding models. So if you go to Hugging Face right now, and if you search Hugging Face embedding models, you'll be greeted with a huge number of embedding models. So here you can see IBM has their embedding model, OpenAI has their embedding model, Cohere has their embedding model. Huge number of labs have their embedding models which have been trained on different data sets and using different architectures. But all of these are large language models. So if someone asks you, where does language models come into the picture in dense retrieval? Well, they come into this stage where we convert queries using an embedding model into a vector. So now I'm not going to comment on which embedding model to choose. I'm just going to describe this process to you. Alright. So then the query is converted into a vector. Okay. And then what is done is that all the possible resulting documents. So let's say we have document number 1, document number 2. Let's say there are 50,000 documents such as this. And we want to find out which is the document which should be shown first when the user asks this query. So if I click on search right now, this document is shown first, right? 10 best shows like Stranger Things to watch on Netflix. So let's say there are 50,000 documents. How to decide which one should be shown first? Well, what's done is that similar to how we converted query into a vector, each of these documents is converted into a vector in the same dimensional space, into a 384 dimensional vector space. All of these documents are converted into vectors. So we have 50,000 documents, 50,000 documents converted into 50,000 vectors. So you have one vector for the query and you have 50,000 vectors for these documents. So let's map them out over here. Let's say if you have query which is mapped here, just for the sake of representation I've projected it into a lower dimensional space, and then let's say this is document 1, this is document 2, and this is document 3. So imagine we have, I'll put one more for document number 50,000. The next thing which is done is that when you have vectors in vector spaces, there are different ways to compute distances between the vectors, right? There is a thing called Euclidean distance. So Euclidean distance would directly be the distance between these two, which is x1 minus x2 square plus y1 minus y2 square. Let me mark out the Euclidean distance in green right now. So Euclidean distance between query and text2 is, let's say, L1. Euclidean distance between query and text1 is L2, and Euclidean distance between query and text3 is L3. Now which one do you think is the shortest? Text2, the distance between text2 and query is the shortest, right? So then that document which has the shortest distance with the query will be presented first. So in the example which I showed, this document here, the 10 best shows like Stranger Things to watch, that will be presented because if this is the one which has the shortest distance. So the shortest distance documents are presented first, and the documents which have a larger distance are shown sequentially below. So if you go to page number 10 right now, no one sees page number 10, right? These are the documents which have, let's say, the lowest or the lowest similarity or the highest distance metric. So this is also sometimes called as the similarity score. Similarity score, or you can refer to it as distance metric. Now there are different types of distance metrics. One more type of distance metric is based on the cosine similarity, right? So that's also, so let's say if you have one vector which is this and the other vector which has this, the cosine of the angle between them is 0, right? So these vectors are very similar to each other. So cos of 0 is 1. On the other hand, if you have vectors who have a 90-degree angle between them, like these two vectors, these vectors will be dissimilar because they have a 90-degree angle and cos of 90 is equal to 0. So these two are dissimilar vectors, whereas the green vectors are similar. That's another way to compute distances. So if, let's say, this is your query vector, then you will always choose those documents which are parallel to the query vector in this case, because the angle is minimum. If the angle between a query and a document is 90 degrees, it means that the query and the document don't contain too much information which is similar to each other, and that's why they are not similar at all, and the distance value is the highest. 90 degree is the highest distance metric in this cosine case. So there are different types of distance metrics you can use. You can use a Euclidean distance as I showed you, or you can use cosine similarity. So in this case, text 2 will be the best result for this query because text 2 has the lowest Euclidean distance as compared to other text with the query. Okay, so here is the sequential process which I just described to you. User enters the search query. We then embed the query in the same vector space as our text archive. What is text archive? It's those 50,000 documents which I just told you about. Let me write it nicely, 50,000 documents. Alright, then what we do is we simply find the nearest document to the query in the vector space. And what is meant by nearest? It can either be the Euclidean distance or it can be the cosine. I am just calling it cosine because that's the angle. Remember, the 90 degree is the means no similarity, and parallel or 0 degrees, which means highest similarity. So actually now let us directly jump into code, and what I'm going to do is that I'm going to have a query, and we are going to use an embedding model provided by a company, and we are going to use dense retrieval to rank the documents, or rather we are going to use dense retrieval to provide the documents with the highest similarity as our vector or our query. In this process I am also going to demonstrate how keyword search does not work very well. Remember, before we came to semantic search, the type of search which was very popular was keyword search. Alright, so let's get started with the code right now. So here is the code. As I have mentioned before in this series also, we are very closely following the lecture series in this book, Hands-on Large Language Model by J. Alamar and Martin Gruthendorst. All of their code base is public online. So if you can just go online and search hands-on large language models, you'll see this GitHub repository. Oops, hands-on large, yeah, this is the GitHub repository where all their code exists. As you can see, within a matter of 3 months, it has around more than 3K stars. So it's a pretty popular repository because they have a huge number of practical projects which can be done. And we are going to see one such project today. Alright, so before we get started, you will need to install some packages. Today we are not going to use LangChain, but just install it because we will need it later. So we will install LangChain, we will install FAISS. This is something which we will come across today. So FAISS is Facebook AI Similarity Search. It's a library for efficiently finding which documents are similar, or vectors corresponding to which document are similar to the main document. You can see it has 32,000 stars, so it's very popular. I'll come to why we need this library later in this lecture. Then one of the most important libraries which we need is Cohere. So Cohere is one such company who provides embedding models. We are going to use embedding models from Cohere today, and for that we'll need something which is called as a Cohere API key. So see, this is what we are going to use, co.embed, which is the embedding models given by Cohere. Cohere is one of the leading AI companies. Here you can see world's leading AI platform for enterprise, and I had not known about them before, and honestly I'm not sure how they compare with other embedding models out there, and so you're open to try those. So OpenAI also has their embedding models. They also have an embeddings API, so you're free to try out this as well. The only reason I'm going to use Cohere is because in this repository, in the hands-on large language models, the researchers have used Cohere, so I thought to go ahead with it. The first thing you will need to do is you will need to sign in here, and once you actually sign in, you can continue with Google and you can sign in, and when you sign in, an API key will be created and you can access that API key. So you can go to API key over here, and you can access your API key right over here. You will need this API key, so save it. I am going to just delete my API key from here. The reason I showed you this is because it's not a good practice to expose your API key. So I have seen many Google Colab notebooks where API keys are exposed. So I have just removed this for now. But that's why you need this library, because we are going to deal with Cohere endpoints, which means that we are going to use embedding models from Cohere today. Another library which we need is rank BM25. So if you search about BM25, BM25 algorithm is one of the leading algorithm for keyword based search. So this is the technique which was used earlier, which is keyword matching. And remember, we want to compare why semantic search is better than keyword search. So that's why we need this algorithm. Sentence transformers we might need later, not in today's lecture, but it's best to run this code so that all the packages are installed. The next thing which we need to do is we need to import the package cohere, and we need to paste our API key over here, and we need to create and retrieve the cohere API key. So this is a cohere.client. So we create a client with the API key, and it's called CO. This is the client which we'll be using to get the embedding models. So imagine the client as that interface which helps us get embedding models from cohere and use it in our Google Colab. Next, the thing which I'm going to use, which is going to serve as our it's called document library. So remember, I told you this 50,000 documents. So we need some kind of a document library, right? So if some query is entered, we need some documents to search to match the query. So the document library which I am going to use right now is a simple text about the movie Interstellar. So if you just go to Interstellar and go to the Wikipedia page, what we have done over here is that basically we have just taken the first 3 paragraphs from here, and we have put this as text over here. So you can choose any text for the purposes of this lecture. As you're following along, you can just run the Google Colab notebook which I'm sharing with you, or what you can do is you can just feel free to explore and use your own text. It will be a lot of fun that way. The next thing what we are going to do is we have to learn something which is known as chunking. So remember, I told you about this document 1, document 2, 50,000, right? So let's say if you get this piece of text, which are these 3 paragraphs, which of these will serve as individual text documents for you? Do you take this entire thing as just one document? Then that's of no use, right? Because then this entire thing will be represented as one vector. So whatever query you enter, always this vector will be returned. We don't want this. We want to analyze every sentence here, and we want to return that sentence which matches the query. So if the query is how much was the revenue collected by this movie, we want this sentence to be returned. So since we want sentences to be returned, every sentence needs to be a separate vector in this document. So every sentence needs to be a separate document rather. So to convert the whole piece of text, so let's say if you have this big text archive, let me call this text archive. We need to convert this text archive into a bunch of documents. So we need to take this text archive and we need to convert it into a bunch of documents. So here see, I have converted into 1, 2, 3, 4, 5, 6, 7 and 8 documents. So there are 8 documents right now. So whenever a query is asked, out of these 8, which one is the closest will be returned. This process of taking a text archive and converting it into individual documents is called as chunking. And if you are running a startup right now, or if you are part of a startup or any company rather which is dealing with text, chunking is one of the most important things and also one of the most difficult things to do. Because the reason it's difficult to do is because there are several options to do chunking. Right now, if I go to this, I can chunk it paragraph wise, which means I can make this as a one vector. I can make the second paragraph as one vector, and I can make the third paragraph as another vector. That's one way to chunk it. Another way to chunk it is just take one sentence, make it the first vector. Take the second sentence, make it the second vector. Take the third sentence, make it the third vector. So there are several ways to chunk. We'll look at different chunking strategies later, but for now we'll chunk it into different sentences. So we are going to use a sentence level chunking, which means that one sentence will be one chunk and each sentence will be converted into a vector. So this is exactly what we'll be doing in code. We have taken this text right now and we are splitting it into a list of sentences. So we also clean up here to remove any empty spaces and any new lines. So we are removing empty spaces, we are removing new lines, and we are maintaining this text list. So wherever there is a full stop, that will be a new sentence which is added to this list. So now what we are doing is that every sentence here is one element of this list, and the list is called as texts. You can even print out this and see that this is a list which contains different text as individual elements. So every sentence is now one document for us essentially. This is sentence level chunking, right? Next, what we have to do is we have to take each sentence. So here we have to take each of these sentences and we have to convert them into a vector. So we have to take each of these sentences and we have to convert them into a vector, right? So for that we have to use an embedding model, and the embedding model is going to be taken from this Cohere client, which is called CO right now. So we are going to use co.embed and we are going to embed these texts, and input type is equal to search document, and we are just going to do .embedding. So it will automatically create embeddings. So if you go to Cohere, you will see different options for different types of embedding models which you need. For now, we are just going to use the default. So we are going to say co.embed and here .embeddings. We pass in our texts and we pass the input type, which is search document. And then what we do is we print out the embeddings shape. So here you can see that there are 15. Why is the first element here 15? Because the text is a list which contains 15 different sentences. So actually this, instead of 8 what I have shown here, there are 15 different sentences. There are 15 different sentences, and each sentence is now converted into a vector which has 4096 dimensions. So each sentence is now a vector with 4096 dimensions, and that's why if I plot it in the matrix right now, this is, let's say, sentence 1, sentence 2, ... sentence 15, and each sentence is now a vector with 4096 dimensions. So right up till the very end it's 4096. So this matrix right here which you see, it has 15 rows and it has 4096 columns. So that's what you are seeing over here. The shape of this embeddings is 15, 4096 because there are 15 rows and 4096 columns. This is our embeddings table right now. So now what will happen is that when you give a query, the query is also converted into its own vector, right? Now that vector will be compared with all of these vectors, and then we'll search which one has the lowest distance, and that will be given as the response. This is the simplest way to explain what we are doing here. Alright, so next what we have to do is that we have to use this library called FAISS, and there is a reason why we are going to do this, and let me explain that to you right now. Although it comes a bit later over here, I think it's important that you know this right now. The simplest way to do this, as I mentioned here, is to just find the distance between the query and each of these vectors, right? So you may be thinking, why do we need a library? The reason we need library is because here there are only 15 sentences, right? But remember that big companies and startups deal with millions of documents. So ideally you need to go through millions of these vectors and look at which vector is the closest with the query. And to do that you need an optimized way to do this, and that is where the FAISS actually comes into the picture. So let me talk about this a bit. As I've said, for small number of vectors we can just use NumPy. And we can just find the nearest neighbors to the query, right? But as we scale beyond millions of vectors, an optimized approach for retrieval is to rely on approximate nearest neighbor search libraries, such as there is one library called Anony and there is another which is called FAISS. FAISS is Facebook AI. I think it's Facebook AI search system. It's a very efficient library, because they do something called approximate nearest neighbor search, which means that even if we have to search through millions of vectors, it's fast. The process is fast. So using libraries like this, it allows us to retrieve results from massive indexes in just a matter of milliseconds. GPUs can further improve this performance. So just keep in mind that you cannot just use NumPy to do this search, to do this finding the nearest neighbor, because it does not scale. You can do this for tens of thousands of vectors, but if you are dealing with millions of vectors, you need to use libraries like FAISS. This is the library, and if you see, FAISS is a library for efficient similarity search and clustering of dense vectors. It contains algorithms that search in sets of vectors of any size. So that's the main advantage of FAISS, speed. And the distance metric which FAISS uses is the Euclidean distance. That's very important. So I'm exposing you to this library because if you're dealing with real projects and real systems, you will have to use the FAISS library for search. So what we are doing over here is that we are importing this library and we have to create something which is called as search index. So right now we have this matrix, right, as I showed to you over here. We have this matrix using FAISS or the Facebook AI similarity search. We have to take this matrix and we have to convert this into something which is called as search index. This makes the nearest neighbor or finding the vector with the closest distance easier and faster. So see, the command which is to be used here is FAISS.indexFlatL2. Why is L2 here? Because it's the distance metric which we are going to use. And then we are going to convert each of the embeddings into a float 32 and we are going to add this to our search index. So first we create a search index through FAISS and then we add all of our embedding table into this search index. So if you look at the FAISS library, you will see the documentation and you will see the commands. So just go through this library. The main thing is you have to create a search index, and for that we have used index FAISS.indexFlatL2. You have to give the first dimension over here. So embeds.shape1, I think this is 4096. So that's the dimensionality of the embedding which you have to provide over here. And then you just do index.add and you create the search index. That's it, right? The next thing what we have to do is that once this search index is created, remember we have to then look at the query. We have to look at the query and find the vector in the search index which is most similar to the query using the L2 distance. So this is what we are going to do next. We are going to define a function which is called as search. It takes the query and it also takes the number of results as an argument. So here we are going to result the top 3 similar vectors. So similar to how we embedded the documents, right? Each of the sentence, we also have to embed the query. So we are going to get the query's embedding and call it query embed. And again, we are going to use co.embed. Here we have to pass in the query. That's it. So actually this is exactly the same code which we used over here. But here just one embedding is created. So we access the index 0. And then what we are going to do, this is the most important function of FAISS. We are going to search our index which we have created over here. And then we are going to retrieve the nearest neighbors. So we are going to search our index with the query and we are going to return 3 results which are the closest to the query. And we are going to format the results a bit. So we'll convert the text to NumPy for easier indexing and then we'll print out the text and we'll print out the distance. So what we are going to do is that when this function is called, we'll print out the query again and then we'll print out the nearest neighbors. And when we print out the nearest neighbor, we'll print the sentence which is closest and we'll also print the distance of that sentence to the query. So imagine here what we are doing, query with, so the distance of the query from the first sentence is, let's say, D1, from the second sentence is D2, with the third sentence is D3, right up till the 15th sentence is D15. What we are going to return is, we are only going to return, let's say, D4, D7 and D8, which are the smallest distances. Only 3 we are going to return. So we'll look at all these 15 and then we'll look at only the 3 distances which are the smallest with the query, because those are the 3 most relevant results to us. So let's actually test this function now. Before that, let's read what is written over here. So Interstellar is this science fiction drama directed by this theoretical physicist, was an executive producer. That's fine. Interstellar was released in theaters. All right. Then there is one more sentence in this thing which says that let's see. Yeah. Yeah, the sentence is over here. It received claim for its performances, direction, screenplay, musical score. It also received praise from many astronomers for its scientific accuracy and portrayal of theoretical astrophysics. Now, this sentence I do not see over here in this Wikipedia. Yeah, it is there. Received commendation from astronomers and physicists, but it's been changed. That's fine because Wikipedia is continuously updating. But here is the text which says that it has also received praise from many astronomers for its scientific accuracy and portrayal of theoretical astrophysics. Okay, then the question which we are going to ask is how precise was the science? This is the query. And all of this is the text. Now, if you go through this text, there is only one sentence which is related to how precise is the science, and that is it has also received praise from astronomers for its scientific accuracy. That's the only sentence which is related to this query. Let's see whether our algorithm retrieves that sentence. So the query is how precise was the science, and then what we are going to do, we are going to just run this function called search on our query and print out the results. So see, there are 3 results which have been printed, and the first result, which has the lowest distance from the query, is it has also received praise from many astronomers. This is exactly the sentence which we are looking at, right? It has also received praise from many astronomers for its scientific accuracy and portrayal. Then there is another sentence which is Caltech theoretical physicist and 2017 Nobel laureate. Here, Caltech theoretical physicist, 2017 Nobel laureate, was an executive producer, acted as scientific consultant, and wrote a book. So our algorithm has identified that that is another document which is closer to how precise was the science, which makes sense because a Nobel Prize winning person was on the team. And then the one which has the highest distance, which means it's not as relevant, is Interstellar uses extensive practical, and so let's see where this is. Interstellar uses extensive practical and miniature effects. So this is not as related to the search query, right? So here we can clearly see that's why the distance is the highest. So our first conclusion from this is that our algorithm, which we have created, the dense ranking algorithm, is actually working. And one thing which I want to mention here is that now I hope you see why this is semantic search. How precise was the science? That's the query. So if you look at the response, which is the lowest distance, that has no keywords which are matching with the query at all. So unless you understand the meaning of this query, it is impossible for you to give a text which matches the meaning, right? And that is the power of transformers. So the way Cohere would have created this embedding model is that they would have definitely used transformers to take text and sentences and to convert these every text and sentence into vectors which capture meaning. So all the magic happens in the way companies like Cohere have created these embedding models, because it captures meaning. Cat and kitten, let's say, would be close together in that embedding space. Dog and a puppy will be close together in that embedding space. And since transformers, BERT model, etc. can be used for this, all of that is now reflected in the results, right? We are clearly able to capture the meaning, how precise was the science, and the response was it has also received praise from many astronomers, praise for its scientific accuracy. Awesome. Which means that semantic search really works. The second conclusion is that embedding models actually work to capture the meaning. So the key magic, so where magic actually happens, where does magic actually happen if you were to think about it? The algorithm is pretty simple. We are just retrieving the vectors with the closest distance or smallest distance, right? But the magic is taking text, taking sentences, taking paragraphs, and converting all of this into vectors. This is where the magic happens. And these vectors are not random vectors, they capture meaning. So two sentences which convey same meaning will be close together in that vector space. So it all depends on how these embeddings are created. That's why if you look at Hugging Face, there are so many embedding models, all with different sizes, all made by different companies, and all with different popularity. Because there are a huge number of ways to create these embedding models. Maybe later I'll make a tutorial on how to create these embedding models from scratch. It's an extremely interesting topic, and it's also widely useful for companies and startups. Alright, the next thing which I want to show you is keyword search and how it does not work as well. So remember, before semantic search came, the BM25 is probably the best algorithm for keyword search, and it has its uses, because sometimes as users we are just looking for matching keywords, right? If I want to search, let's say, about push and pull request, so if I want to search about pull request GitHub, I just want articles which contain about this thing, which contain about these keywords. So keyword matching is useful, but let's see how it does in this particular case. So we are going to use this package called rank BM25, and from this package we are going to use BM250K API, BM250K API. So what we'll do, first we'll define this tokenizer, which takes all of our paragraph and converts it into tokens, which are individual words essentially, and we get rid of common words like the, etc. Then when the tokens are created, we are going to use this BM25K API, and then what we are going to do is that the BM25 algorithm, it then looks at these individual tokens, and it's going to compare them with the query. So it first tokenizes the query, and then it compares that with the individual tokens, and then we are going to return those tokens or those sentences which have the highest score. Basically this is called as BM25 score. I am not going to go into the details of how this works, but I just want to show you the results of this. So if we use BM25, which is keyword based search, here are the top 3 results. So I am going to use the same search query, how precise was the science, but let's look at the results. The first thing which is shown is that Interstellar is a 2014 epic science fiction film co-written. I think it's predominantly shown because science and science are matching, but you see it does not have any relation at all to the question which was asked. The question which was asked was how precise was the science, and the answer here is Interstellar is a 2014 epic science fiction film. So you see here keyword matching, that's why it fails. It does not capture the meaning of what's asked in the sentence. What is asked is how precise is the science. There is no use comparing or matching keywords. Even actually the second one is good, because the Caltech theoretical physicist also came in over here. And the third is it stars Matthew McConaughey, etc. It's not related at all to science. So here we can see that the BM25 algorithm actually fails, and it does not do as well as semantic search. That's another takeaway from today's lecture, that dense ranking, which we have learnt about today. Let me go back. Yeah, dense retrieval. Sorry, I should call it dense retrieval. What we have learned today relies very heavily on the concept of embeddings. That's where the true magic happens. Without embeddings, if we just go with keyword search, the results are not as good. And what makes embeddings possible? It's transformers, it's the large language model revolution such as BERT, etc. So the LLM revolution is at the heart of these concepts of embeddings, which in turn is at the heart of dense retrieval, which is at the heart of Google search. So you see how all of these concepts are related. Large language models completely changed everything, and it affects us because it affects the search. Google search is such a key thing in our lives, and transformers, BERT and embeddings play a major role in that. Sometimes we forget to appreciate this. Alright, now as we move ahead with dense retrieval, there are some design choices which we need to make, right? The first thing is, how did we decide to just give the top 3 results? It could be top 1, it could be top 5, it could be top 10. That's the design choice which we have to make. So that's a decision for you, the system designer. It's sometimes desirable to have a max threshold of similarity score to filter out irrelevant results. So instead of just saying that I want top 3 results, just look at the distances and say that I want anything which has a distance less than 11,500, let's say. That's another way to filter the number of results which you get. Okay, so now another thing which I want to mention is that are a query and its best result always semantically similar? Not always. Currently they were semantically similar and we got good results, but it all depends on how the embedding model is. That's why there is also this process of embedding fine tuning, which makes the embedding process better. So this embedding tool will not work magically. There are a lot of models which you need to try. Some model works better than others. It's always the heart of which embedding model will work is how the language models were basically trained. Right, and the language models which were trained on more question answer pairs and who were trained and fine tuned in a detailed manner, they will always work better. Okay, now we saw different things related to dense retrieval, right? So you might be thinking, wow, this is such an amazing technique, but what about the drawbacks? Dense retrieval does come with its fair share of drawbacks, and one of the most important drawbacks is that even if the text does not contain the answer, there is still some answer which is given by dense retrieval. So let's say the text is completely random. So if the question was how far, in fact I've done this over here. So if the question is what is the mass of the moon, this is not related to the text at all, right? The text is about interstellar film. But if you search the results, if you search this query and find out the results which are most semantically similar to the query, you do get results which do not make any sense at all with the query. So the film had a worldwide gross over $677 million. How does this make any sense to what is the mass of the moon? That's one main disadvantage of dense retrieval. Unless you specify that distances above a certain threshold should never be returned, it will always return some answer. So as I mentioned, one solution to this is to set a distance level threshold, to set a threshold level. So if the distance is above that threshold, the answer will never be returned. It will say that nothing matches your query. Another issue is that when a user wants to find exact match for a specific phrase, so sometimes, as I mentioned, keyword matching is the best way to go forward, because sometimes users want the exact match to the phrase, right? They don't want meaning. Sometimes if you are just looking for an encyclopedia meaning, you just want the perfect match for the keyword. So then usually what people prefer or researchers prefer is something called as a hybrid search. So hybrid search is a semantic search plus keyword search. So then what you can do is you can use a mix of, let's say, right now we saw dense retrieval, right? You can use a mix of this plus BM25, the BM25 algorithm which we saw. So keyword matching is not that you will never use it again. It's very useful if you want to find exact keyword matching. But if you want the best of both worlds, then hybrid search is used, which is the mix of semantic plus keyword search. Another drawback of dense retrieval systems is that dense retrieval systems find it difficult to work in domains other than the domains they were trained on. So for example, if we train a retrieval model on the internet and Wikipedia data, let's say, and deploy the retrieval model on legal texts, without having enough legal data in training, the model will not work as well. So let's say we have trained the model, and when I say trained the model, it means trained the embedding. To create the vector embeddings, remember we have used this Cohere embedding model over here, right? To create this model, Cohere has trained it on data, right? Now, if this training, let's say, is on Wikipedia data, and if the query which you ask is on legal system, which was not part of the training data too much, the retrieval will be not good, because the legal system data was not part of the training at all. And that is one disadvantage of dense retrieval. And that disadvantage is that if you don't have training data which is sufficient enough, and if you ask a question about something which is not there in the training data, the answers will be completely random. So there are these three disadvantages you have to think of. The first disadvantage is, what if the text don't contain the answer? That's the disadvantage. The way to get around this is to set a distance threshold level. The second is, what if a user wants to find the exact match for a specific phrase? Then you can use a hybrid approach of semantic plus keyword search. And the third is, sometimes dense retrieval systems find it difficult to work in domains other than the ones that they were trained on.